Now, in this lecture, we shall learn about the first, the applicability of AS1170 codes. So right now, we are dealing with the AS1170, and this code is a code which is basically divided into 5 parts. So AS1170, we can say part 0, that basically deals with the, we can say, general principles. So AS1170 dot deal 0, that deals with the general principles. After that, we are dealing with the AS1170 part 1, that deals with the permanent, imposed, and other actions. So this was also a name change, we can say, in the earlier code. Permanent load was basically named as a dead load. Imposed load was earlier named as the live load. That is, if we are talking about the weight of the structure itself, that shall be classified as a permanent load. But when we are dealing with the residence of that particular building, or let us say if we are talking about the hospital, the weight of the patients, or the weight of the doctors that are occupying that building, that shall be classified as the imposed load, and other actions. Similarly, when we are dealing with the AS1170 part 2, that basically deals with the wind actions. And one more thing, in the earlier code, we were using the word loads. Like when we refer to the old codes, we name it as loads. But now in the in latest codes, it is named as action. So that is why we shall be also dealing with the permanent, imposed, and other action. AS1170.2 deals with the wind actions. AS1170 part 3 deals with the snow and ice actions. AS1170 part 4, that basically deals with the earthquake actions in Australia. Earthquake actions in Australia. And when we are dealing with the AS1170 part 5, we shall be dealing with the earthquake actions in New Zealand. So these are the 5 parts of AS1170 code that basically deals with, we can say, actions. Now in this lecture series, we shall use the word loads and action also. They both basically mean same only. And all of these codes have been, undergone various amendments, also various revisions also. So we shall be targeting that we should discuss in the latest code as on today, that is August 2023. So first of all, when we are dealing with the loading action, the first, or when we are dealing with the Australian standards, the first code that we do need to read is AS1170 part 0. So that basically deals with the general principles. So these general principles are also like very important, because this is the code, like for New Zealand, this is the code which basically guides us on what exactly should be importance level and what exactly should be the reliability index and all of these terms. And those we shall discuss the individually, or we can say whenever the turn comes. Now, first of all, we shall start with AS1170. And we shall be, it shall be better if you can also open this code in front of you on section 1. When we are dealing with this particular code, we are dealing with various actions. In building, when we are dealing with any kind of building, we shall be dealing with various kind of loads and actions. So what are the various kind of, loading and actions that can come onto a particular building? It may be, we can say, permanent load. So as I said, that permanent load basically deals with the self weight of the structure, or let us say, there are these brick wall also, or we can say block work also. And on the top of that, let us say there is this shed also, or we can say steel beams also that are fixed on the top, and on the bottom of it, basically, let us say there is this basement structure, and below that there is this foundation. So weight of all of these, we can say that basically accounts for the permanent load. And after that, let us say when we are dealing with the imposed actions. Imposed actions means the live load. So we can say that, let us suppose this building is being occupied by some persons. So if if they are moving in this building, or if they are sitting in some part of that particular building, so that basically accounts for the imposed action, that is live load. Third part is the, we can say, wind action. So let us say in the case of an extreme wind, the wind is flowing, and that is also putting pressure on that particular building, or on the roofing, or on the side wall sheeting. So that basically accounts for the wind action. After that, the fourth action that we shall be dealing with is snow load. Like in many parts of New Zealand, it snows a lot. So in those particular buildings, we have to ensure that under the case of snow, that the roofing can take the load. So that is also like one of the loading that we do need to attend to when we are designing the buildings. After that, fifth load is the earthquake load. Now, in majority of the structures, or we can say broadly, if we're talking about the Australia, in Australia, wind action is the one that usually governs the design. So in Australia, we can say that usually, that is my experience. So wind action is the one that usually governs the design. But when we are dealing with the New Zealand, it is usually the earthquake load that governs the design of the building. Governs the design means that the if we are talking about the beams, if we're talking about the columns, they are basically governing or getting critical in the case of earthquake load when we're dealing with the New Zealand. And most of the building component design, let us say beam, column, slab, brickwork, etc., they are being governed by the wind action when we are in Australia. After that, when we are dealing with the static liquid pressure. So in here we are saying about the static liquid pressure, because there is also a term known as the dynamic liquid pressure. So when we are dealing with the water tanks in New Zealand, or when we are dealing with the structures that are above the ground and carrying very large volume of liquids, so in that case, dynamic liquid pressure is usually accounted for. So there are these various, we can say, codes that also help us in calculating the dynamic liquid pressure. But if when we are dealing with Australia, it is mostly the case where we have to deal with the static liquid pressure. And when we are in New Zealand, we mostly have to deal with the dynamic liquid pressure. Now, dynamic liquid pressure is like, as I said, that we may be talking about the water tanks. So in those water tanks, maybe the liquid is kept inside. So at the time of earthquake, what happens is that liquid, it experiences movement inside. So due to its self-weight and or due to its inertia, it is that additional side pressure is put onto the side of this water tank. So that that is again a very detailed engineering that I shall not be able to explain in this particular lecture, but definitely I shall be dealing with that in a separate lecture. So static liquid pressure and dynamic liquid pressure. After that, the next loading is basically the groundwater. So groundwater, when we are dealing with, let us say we are designing a building, and let us say this is basically the basement area, and this is the foundation. So if the water table, the groundwater table in this particular area, that is above this foundation, so due to its buoyancy, we can say it shall put uplift pressure onto this building. So buoyancy is the, we can say, force or after effect of the groundwater. And I can say that many times it too happens that if it is not accounted for, this building can get, we can say, uplifted also from the foundation if the groundwater table is very high or the groundwater pressure is very high. So we do need to account that also. After the rainwater ponding. Now, when we are dealing with the process of rainwater ponding, sometimes it too happens that, let us say, this is the steel building that you have designed, and these are the steel columns. This is basically the steel beam. Now, let us say at the time of the rainwater, this or due to the rainwater load, this beam, it gets deflected in this particular profile. So what will happen is that in this particular area, the rainwater shall, or we can say rainwater shall put additional pressure onto this, because as a steel, as a material, it is bound to deflect as this particular shape. So we do need to ensure that by considering the rainwater ponding action, we do need to ensure that it does not deflect much. Second thing is that we do need to provide the good drainage facilities, like providing rainwater pipes on the edges, so that the rainwater does not get accumulated on the top. Because there are times, there are structures which have failed because of the rainwater ponding action also. What happens is that rainwater gets accumulated here, and ultimately over a time, due to the severe deflection, it can basically collapse also. So that we do need to consider while designing. After that, the last term, the earth pressure. So for calculation of the earth pressure also, the various separate code is given, which help us to calculate the earth pressure. And when we're dealing with the earth pressure, let us say we are designing the retaining walls. On the retaining walls, let us say this is on the right hand side, this is the soil mass that we do need to support. And on the left, this is the level. So this, we can say, difference that has to be, provided, or this whole soil that shall put earth pressure onto this particular, we can say, retaining wall. So this retaining wall has to be designed for the lateral pressure. So this also we shall discuss, that how we can design the retaining wall for earth pressure. And this is also static also and dynamic also. So when we are dealing with the earth pressure, or we can say when we are dealing with retaining walls in Australia, we shall mostly deal with the static earth pressure only. But when we are dealing with the retaining walls in New Zealand, it is better that we do consider dynamic earth pressure, especially in high seismic zones. And mostly internationally in most of the countries, when we are dealing with the, we can say, dynamic earth pressure, we are dealing with the Mononobe-Okabe method. Mononobe-Okabe method. So that gives us basically different, values of the active earth pressure, dynamic earth pressure, and dynamic active earth pressure, and dynamic passive earth pressure. So both of these equations are different, and that basically depends on to the inclination of the, we can say, soil profile, and inclination of the or we can say repose angle. So all of these terms are dealt with, and that is basically designed with the help of the Mononobe-Okabe method. Now that was the basic introduction to the types of loading that we shall be dealing with when we are talking about the AS1170. And we already studied about the various parts of AS1170. Now one of the term that is a very important when we are dealing with the design of the building, that term is basically design working life. Design working life. So when we are designing the structures, before starting, or before we are at the starting level, we have to find out that we have to design the structure for how much time. Usually the design working life for, we can say, normal buildings is 50 years. But when we are dealing with important structures, we shall target for design working life of 100 years. So what exactly can be the definition of design working life? So it can be the duration of the period during which a structure or a structural element is assumed to perform for an intended purpose with expected maintenance, but without any major structural repair being necessary. So we can say that, let us say we have designed a structure, and this is the steel building that right now we are dealing with. This is these are the steel columns. This is basically the steel beam. This is the concrete pedestal, and this is the foundation. Or we can say this is the concrete column, and that is basically supported onto the foundation. So when we are talking about the design working life of, let us say, 50 years for this particular structure, so it has to be ensured that during these 50 years, if you're talking about complete structure, or if you're talking about, let us say, this column itself, so this column has to perform its intended purpose. The purpose is to support the beam on the top. So the purpose is to support basically this beam on the top with expected maintenance that can be done. Like after 20 years or 25 years, we can say that a little bit maintenance may be required, a little bit resting may happen, or we can say a little bit paint job is required after 4 to 5 years. So that maintenance can be done, but it is not that the replacement has to be done for this particular column, or it has to be simply removed and a new steel column has to be installed. That is not the intended purpose. So that is a basic definition of design working life, that we shall be targeting for a structure with structural elements such that they serve their intended purpose without major structural repair. Without major structural repair. So that is the basic definition of, we can say, design working life. So, and as I said that usually they are usually either it is most of the times it is 50 years, but it may go as high as 100 years also, and it may go as high as 200 years or more also, depending on the the importance level of the building. Let us say if we are targeting special structures like major dam or extreme hazard facilities, so those structures have to be designed for, we can say, importance level of very high importance levels, and intended life of 100 years or more also. So that was the basic introduction to, we can say, section 1 of AS1170 part 0. So right now we have studied section 1 of AS1170.0, which basically deals with the title as scope and general. So now we have dealt with the various kind of loading that shall be coming onto the structure, and general terms like what exactly we mean by the design working life, and so in the next lecture we shall be dealing with the section 2 of the AS1170.0, that is structural design procedure.